Hello friends, I am Dr. Sudhan Sharma from School of Computer and Information Sciences, Indira Gandhi National Open University. In our previous sessions, we had discussed about limits and continuity, and we also understood how they are related to differentiation. We also understood about how differentiation is to be performed, and we learned about chain rule, and we learned about how to perform differentiation for the exponential and the logarithmic functions. Now, in this session, we are going to understand about simple applications of the differential calculus. This is the first session in this series. We are going to have two sessions to understand about the applications of the differential calculus, wherein we are going to cover determination of local maxima and minima, understanding what increasing and decreasing functions are. Apart from this, we are going to solve some of the practical applications of differential calculus with the help of few numericals. The objectives of the today's sessions are in fact that after going through this session, you will be able to compute the rate of change of one quantity, knowing the rate of change of some other related quantity. Apart from this, we are going to understand how to determine when a function is increasing or decreasing. In this session, we are going to understand that how to apply the concepts of differentiation in solving the real world applications, because differential calculus actually deals with the rate of change of quantities. That means we are supposed to cover how the variation of one variable is happening with the variation of other variable. In order to understand this, let's see that we are having a coordinate system, say x and y is function of x. That means y is dependent on the values of x. So x is independent variable and y is dependent variable. So how as x varies, there will be variation in the values of y, because y is equal to fx. So say some trend is followed, that means with the variation in x, certain there is variation in y, there with variation in x there is some variation in y. So that means there is per unit variation in x, there is variation in y, so there is y by x, that is with the variation in y, with the variation in x there is variation in y. So dy by dx represents variation in y, variable y, with variation in variable x. And many a times there is a situation that one variable varies with time and the other variable is dependent on another variable. Say I want to say that variable x varies with time, so there is a variation, there is dx variation in time dt, and y also varies with the variation in x. So there is a variation in y with respect to variation in x. So using the chain rule, we can find that how y varies with the variation in time. So rate of change, it is to be noted that the term rate is generally used when there is a variation in variable with respect to the time. But in general, when there is a variation in one variable with respect to some space, that means not time, then we are using the term gradient. We are not going into those details. We are simply going to cater the term rate of change of quantities. That means variation of the variable with respect to the time. So I hope you understood that what is f dash x. Now f dash x is the derivative, and we learned that derivative is dfx by dx. And since y is equal to fx, this is nothing but dy by dx. So dy by dx is nothing but first derivative, and this represents this dy by dx. If from the point of the geometry you want to understand, this is nothing but the slope. This is the variation dy, this is the variation dy, and this is the variation dx. So the slope tan theta is actually variation in y with variation in x, that is dy by dx. So that means it is the first derivative. The derivative of the function represents the slope. This we represent the slope of the curve, which is given by the function fx. So, it is very simple to understand that f dash x is nothing but dy by dx at some point. From the point of understanding of say physical environment, say there is some object which is moving with some speed. Now, what do we mean by speed? Speed means that the object is covering some distance in some time t. So, that means if we are going to plot the curve, say that there is a time variable and there is a distance variable, and the object is covering some distance with respect to, as time increasing, the object is moving. So, that means there is a variation in distance with respect to time, and this variation in distance is equal to upon time is nothing but the speed of the system. And we all know that speed is nothing but distance upon time. So, distance upon time, that means change in distance upon change in time represent the speed of the system. And we also learned about the concept of the chain rule, and which is already explained that if say variable x varies with time dt, varies with time, and in time dt it changes with by the value dx. So, the variation will be represented by dx by dt. And we are having a variable y which is also dependent on x, such that as x varies then y also varies. So, the variation of y with x will be represented by dy by dx. So, by applying the chain rule, we are actually calculating the variation of variable y with the time t. So, this is dy by dt is equal to dy by dx into dx by dt, and dy by dx is nothing but the first derivative with respect to x. F dash x is nothing but derivative of fx with respect to x, that is dy by dx. I hope you understood why we explored chain rule, what is differentiation, but now we are going to apply this understanding to solve some of the real life problem. Likewise, over here the question is spherical balloon is being inflated at the rate of 900 cubic centimeters per second. Watch the unit, cubic centimeters per second, that is variation with respect to time. How fast is the radius of the balloon increasing when the radius is 15 centimeter? So, there is a balloon. Now, balloon is a spherical entity. Balloon is a spherical entity. So, volume of the sphere is to be taken into consideration, and volume of the sphere is 4 by 3 pi r cube. And we are supposed to we are asked how fast the radius of the balloon is increasing when radius is 15 centimeter, and we are given the rate of change when of volume is 900 cubic centimeter. That means, we are given dV by dt, that is equal to 900 cubic centimeters per second. So, that means in order to calculate dV by dt, we are supposed to differentiate equation 1. So, differentiating, we are supposed to differentiate equation 1 with respect to time. So, with respect, differentiating with respect to time, so dV by dt, that is d dt of 4 by 3 pi r cube is to be calculated. So, that turns out to be, by applying the formula d dx of x to the power n is equal to n x to the power n minus 1. By applying this formula in this, you will get 4 by 3 pi is common, and you will be getting 3 r square into dr by dt, which is this expression. So, solving it, you will get it equal to 4 pi r square dr by dt. And we are what we are asked for is how fast the radius of the balloon is increasing when the radius is 15 centimeter. That means, we are to calculate dr by dt. We are to calculate dr by dt. So, that means we can rearrange this equation and we will get dr by dt is equal to, because dv by dt is given by equation number 1, and equation number 1 dv by dt is nothing but 900 units. So, dr by dt is nothing but dv by dt divided by 4 pi r square, and we are asked when r is equal to 15 units. So, dv by dt is nothing but 900 and 4 pi r square means r given is 15. So, 15 square is to be calculated. So, substituting the values and solving, you will get the answer 1 by pi centimeter per second. So, this is what you are getting, and this is the rate at which the radius of the balloon is increasing. This is the rate at which the radius of the balloon is increasing. Now, to further explain, so now let me further extend the understanding that we are given dV by dt is equal to 900 cubic centimeter per second, and we calculated dr by dt equal to 1 by pi centimeter per second. So, many a times say we want to know that how the volume is varying as the radius is varying. So, that means if somebody wants to know how the volume of the balloon is varying as the radius is varying. So, if we are inflating the balloon, the radius will be increasing. So, with the increase in radius, how the volume is varying. So, you may recall that by applying the chain rule, we can write this dV by dt as dV by dr into dr by dt, and dr by dt is nothing but 1 by pi as calculated, dV by dt is nothing but 900, and variation in volume with radius will be given by dV by dr. So, variation in volume can be calculated as dV by dr is equal to 900 into pi. So, by this rate the volume will be varying with the radius. So, you can apply chain rule to find the variation in one variable with respect to the other variable. I hope you understood that how the concepts of the differentiation can be applied to solve some of the real world problem. We are going to solve sufficient number of real world problems so as to make you understand that how the concepts are being applied, and these problems and this type of problems are many a times asked in the examinations also as well as into your assignments, and few more problems are also given into your self learning material, and I again suggest you to go through the self learning material and exercise for such problems. The next problem over here is the example number 2. It is said that a rock is thrown into a lake producing a circular ripple. The radius of the ripple is increasing at the rate 3 meter per second. How fast is the area inside the ripple increasing when the radius is 10 meter? So, just by reading the question, there are two important observations, that rock is thrown into the lake. So, circular ripples are produced. And second important observation, radius of the ripple is increasing at the rate of 3 meter per second. So, there is a circle and the radius is increasing at the dr by dt is given to you, that is 3 meter per second, and it is asked how far the area inside the ripple is increasing when the radius is 10 centimeters. So, the area of the circle that is A is equal to pi r square is increasing with the radius. So, that means the area is varying with radius, and we are given dr by dt. So, in order to connect dA by dr with dr by dt, we are supposed to apply the chain rule. That means, we are supposed to write it uh, 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 like this: dA by dt is equal to dA by dr into dr by dt. and dr by dt is given to us, that is 3 meter per second. So, I hope you understood that why we had used the chain rule and how to understand the problem statement. Now, let us solve this numerical. So, the first observation is that there is a circle. So, circle has got the area pi r square. So, area A is equal to pi r square. Now, differentiating both sides of this equation number 1, we are getting with respect to time t, dA by dt is equal to 2 pi r into dr by dt. And we learned that dA by dt can always be expressed dA by dr into dr by dt, which is nothing but your chain rule. And we are given that r is equal to 10 units and dr by dt is given to us as 3. So, that means by substituting, we are asked how fast the area inside the ripple is increasing when the radius is 10 meters. So, that means dA by dt, we can substitute the values in this equation number 2, the value of dr by dt, that is equal to 3 and r is equal to 10, and you will get 2 pi into 10 into 3, that is equal to 60 pi. So, that means area is increasing at the rate of 60 pi square meters per second. So, this is the rate at which, this is the rate which is by which the area is increasing inside the ripple. Now, again one more question is there. A moth ball evaporates at a rate proportional to the surface area 4 pi r square. So, show that radius decreases at a constant rate. So, we are given a moth ball. So, moth ball is spherical in nature and it is evaporating. So, that means the volume of the moth ball is reducing, and it is given that it is proportional to the area 4 pi r square. So, volume of the moth ball, because it is sphere, V is equal to 4 by 3 pi r cube. And because it is evaporating, the volume is reducing with respect to time. So, we are supposed to calculate dV by dt. And it is given that, read the statement again of example 3. If a moth ball evaporates at the rate proportional to the surface area, dV by dt is proportional to 4 pi r square. And because it is decreasing, the radius is decreasing. So, the proportionality constant should be negative in nature. So, that is why in order to replace the proportionality sign with equal to sign, you are supposed to use the constant which is negative. So, dV by dt should be equal to minus k times, which is a constant of 4 pi r square. So, I hope you understood why this expression is written. Now, V given to us by equation number 1 is 4 by 3 pi r cube. So, differentiating equation number 1 with respect to time, you will get dV by dt is equal to 4 by 3 pi r cube, pi r cube, let me redo it, will be 4 by 3 pi into 3 r square. So, 3 will be cancelled out. So, and apart from this dr by dt is to be there. So, hence dV by dt will turn out to be 4 pi r square into dr by dt. And by this equation, by the equation number 2, which is written over here also, dV by dt is equal to minus k times of 4 pi r square. So, by comparing equation number 2 and equation number 3, in equation number 3, we can say, this is equation number 3, we can say 4 pi r square into dr by dt is proportional to or is equal to minus k times of 4 pi r square. So, that means this component will cancel out and you will find that dr by dt is minus k, this which represents that the radius is decreasing. And for that reason we are having the negative sign. So I hope you understood that how we applied the concept of differentiation to solve this problem. Now, few more problems are there and the level of difficulty is increasing because these problems are supposed to be integrated with the real life problems. So, example 4 is there and which says that a young child is flying a kite which is at a height of 50 meter. So, a child is there and read the statement, a young child is flying kite which is at the height of 50 meters. The height of the kite is 50 meters. So, 50 meters is the height. The wind is carrying the kite horizontally away from the child. So, wind is carrying the kite away from the child with the speed of 6.5 meter per second. So, the speed of the air is given that 6.5 meter per second. How fast must the kite string be let out when the string is 130 meter? So, string length is given to you and after that it is asked that at what rate the string must be let it out. So, if we say that h is the horizontal distance, if we say that this distance, this horizontal distance of the kite, say kite is, child is here, kite is here, okay, and this is the distance. So, we say that the vertical distance is 50, vertical distance is 50 and the horizontal distance is h and the vertical distance is 50 and say this length is L. Then applying the Pythagoras theorem, you can always say hypotenuse square is equal to base square plus height square, that is h square plus 50 square. Now, we are given that the speed, the wind is carrying the kite horizontally away from the child at a speed 6.5 meter per second. So, that means dh by dt, horizontally this horizontal distance is increasing at the rate of 6.5 meter per second. So, this is given to us that dh by dt is nothing but 6.5 meter per second. So, we are given dh by dt is equal to 6.5 meter per second. So, that means we need to differentiate this equation number 1 with respect to the time. So, differentiating with respect to time and applying the formula ddx of x to the power n is equal to nx to the power n minus 1. So, differentiating both sides you will get 2L into dL by dt is equal to 2h into dh by dt, which is this expression. Or you can say that L into dL by dt is equal to h into dh by dt because 2 will cancel out from the both sides. We are already given dh by dt 6.5 meter per second and we are also asked that how fast the kite string be let out when string is 30 meter. So, that means L given to us is 130 meters. So, by using this equation number 1, you can always find what is the value of h because L square is equal to h square plus 50 square. So, h square will be equal to L square minus 50 square, that is 130 square minus 50 square, that turns out to be 120. Solving you will get h is equal to 120. So, we are having L is equal to 130, h is equal to 120, dh by dt given to us as 6.5 meter per second. So, using all these expressions in equation number 2, you can always find that dL by dt is equal to h by L into dh by dt. You know h, you know L, you know dh by dt. Substituting the values in this expression, equation number 2 and solving, you will get dl by dt is equal to 120. 120 is your h, 130 is your L, 6.5 is dh by dt. Solving, you will get 5 meter per second. So, this is the rate at which the kite string must be let out when the string is 130 meter. So I hope you understood that how we solve this numerical. Now, one more numerical is over there that say you need to understand the statement. Transform, read the statement cautiously, transform the statement into the mathematical expression and try to understand with respect to whom it is to be differentiated. You are supposed to practicize that how to transform the mathematical statement, transform the English statements into its equivalent mathematical version. That's why we are solving these many problems, so that you learn how to transform English statements into mathematical equivalents. In this example number 7, it is given that sand is poured into a into a conical pile. So conical pile is shown over here, and it is having height h and radius r, and A is center and B is the extreme part. Sand is being poured into conical pile at a constant rate of 50 cubic centimeters per minute. So it is the rate at which the sand is poured is 50 cubic centimeters. So we are given dV by dt. The rate at which the sand is poured is 50 centimeter cube per minute. Frictional forces in the sand are such that height of the cone is always 1/2 of the radius. So height of the cone is always 1/2 of the radius. This is the second important information. And what is conical pile is there. So volume of the cone is to be taken care into consideration. So 1/3 pi r square h is the volume of the cone, which is the first observation to be taken into consideration. Second important observation is 50. What is the rate is 50 centimeter cube per minute. Third important observation is that height of the cone is always 1/2. So this is the third important observation of the radius of the base. So what is the radius of the base is r, and what is the height of the cone is h. So that's why h is equal to 1/2 of r. How fast is the height of the pile increasing when the sand is 5 centimeter? So what we are supposed to find? We are supposed to find dH by dt. We are supposed to find dH by dt. So I hope you understood that how we are transforming the English sentences into its mathematical equivalent. Now let's solve it. So we are given uh, so using equation number 3. So by equation number 3, h is equal to r by 2. So r is equal to 2 times of h. This is equation number 4. So using equation number 4 in equation number 1. So using 4 in 1, you can always write that v is equal to 1/3 pi into 2h whole square into h. That will turn out to be 4/3 pi h cube. So we had replaced r is equal to 2h in this equation, and we got volume is equal to 4/3 pi h cube. Now dV by dt is given to be 50 centimeter cube per minute. So we need to differentiate this expression, this volume, that is 4/3 pi h cube, which is equation number 5, with respect to time. Then by differentiating and again following this formula ddx of x to the power n is equal to x to the power n minus 1, then you will get the formula, you will get the solution. 4/3, that is dV by dt, will be equal to 4/3 pi into 3h square into dH by dt. So dH by dt is to be found, and we are given dV by dt. So we are given dV by dt as 50. So substituting the value of dV by dt equal to 50, you will get the expression, that 50 is equal to 4 pi h square dH by dt. Now, the one more important information was, the question was how fast the height of the pile increases, that is dH by dt is to be computed when sand is 5 centimeter deep. So, h is 5 centimeter. When h is equal to 5 centimeter, at this point we are supposed to find dH by dt. So, that means referring to this equation, equation number 6, we can rearrange it and we can say that dH by dt is equal to 50 upon 4 pi h square. Now, because at h is equal to 5, it is required that what is the rate of change of height. So, substituting substituting 5 in place of h, you will get dH by dt is equal to 50 into 4 pi into 5 square. So, that solves to 50 upon 100 pi, and that is nothing but 1 upon 2 pi. So, height of the cone is rising at the rate of 1 upon 2 pi centimeters per minute. I hope you understood how to solve such type of word problems. Now, the next important concept is how to find that whether the function is increasing or decreasing. So, again, in order to understand this concept, let me draw a curve for you. Say this is a curve. Now, in this section, there are two sections of this curve. Say, you can say that these are the sections. In the first section, the slope is this, and that means with the variation in x, as x varies, y is also varying, and you can see the trend that as x varies, y is increasing, as x is increasing, y is increasing. So, that means dy by dx is greater than 0. So, you can say on the other lines that as x1, looking at this expression, that as x1, as x is increasing, y is also increasing, and y is nothing but fx. So, if x1 is less than x2, then fx1 is also less than fx2. That means the pattern which is followed is increasing pattern. So, a function is said to be increasing if in any interval for say any two values x1 and x2 in that interval, we are finding the pattern that if x1 is less than x2, and we are finding the pattern that fx1 is also less than fx2, then the function is increasing. But if we are finding the expression that x1 is less than x2, but fx1 is greater than fx2, likewise in this section, you can see that x value of x is increasing, but value of y is decreasing, value of y is decreasing, value of y is decreasing, value of x is increasing. So, in this section the slope is negative, that means the function is decreasing. So, it is very simple to watch through the graphs that if the values of x are increasing, if the values of x are increasing and the corresponding value of the function are also increasing, then the function is increasing. And if values of x are increasing, but the corresponding value of the function are decreasing, then the function is decreasing. So, I hope you understood this. Now, this is again the graphical representation that in this section you are finding that value of x is increasing, but the value of y is decreasing. So, in this section the function is decreasing, but in this section with the changes in the value of x, there is no change in value of y. So, the function is constant, and in this section the variation, there is no variation in y with respect to variation in x. So, function is, the variation is 0, the derivative is 0, and derivative of a constant is always 0. So, that is why in constant region we are supposed to check that whether the derivative is turning out to be 0. If it is turning out to be 0, that means there is no variation in variable y with respect to variable x. In this section, the variation in y with respect to x is there and it is less than 0. Apart from this, in this section, as x is increasing, we are finding that y is also increasing. So, that means dy by dx, that is the derivative, is greater than 0. That means for the increasing functions, the derivatives are greater than 0. For decreasing functions, the derivatives are less than 0, and for constant part, the derivatives are equivalent to 0. So, if values of x are varying, say x1 is greater than x2 and fx1 is also greater than fx2, then the function is increasing. If x1 is less than x2 and fx1 is greater than fx2, then the function is decreasing. So, let us solve one numerical. So, example over here is that show fx is equal to 3x plus 2 is increasing function. Now, since 3x plus 2 is a linear expression, and by say x1 and x2 are the two values which are say belonging to a set of real numbers, such that x1 is less than x2, x1 is less than x2, you can always find that 3x1 plus 2 is always less than 3x2 plus 2. So, that means fx1 is also less than fx2. That means fx2. So, this means the function is increasing. By looking at the graph, say for value x1, you are finding that the value is fx1. For value x2, the value is fx2, and which is significantly higher than the previous value of x1. So, from the graph also it is find that fx1 is less than fx2, wherein x1 is also less than x2. So, the function itself is an increasing function. So, there is a theorem which we had already discussed, that if first derivative, that is f dash x, is greater than 0 for all the values of x belonging to an interval a b, then the function is increasing. Similarly, if the derivative f dash x is less than 0 for all the values of x in an interval a b, then the function is decreasing. So, for increasing functions, the first derivative of x should be greater than 0, that is dy by dx should be greater than 0, and for decreasing functions, the derivative of x should be less than 0, that is dy by dx should be less than 0. So, say we are supposed to apply now this understanding to solve some more numericals. Now, over here the question is, determine for which value of x the following functions are increasing and for which value the functions are decreasing. The first function given to us is 16x square plus 3x plus 2, and determining the derivative. So, fx given to us is 16x square plus 3x plus 2. So, the first derivative f dash x turns out to be 32x plus 3. We are simply applying the formula ddx of x to the power n is equal to nx to the power n minus 1. So, ddx of x square turns out to be 2x. So, that means, and 2x into 16, it turns out to be 32x, and derivative of 3x turns out to be 3 only. So, f dash x is 32x plus 3. Now, if the function is increasing, then the derivative should be greater than 0. So, that means 32x plus 3 should be greater than 0. That means, rearranging, you can say that x should be greater than minus 3 by 32, and for f dash x to be less than 0, but the region for which it is decreasing, then 32x plus 3 to be less than 0, that means x to be less than minus 3 upon 32. So, you can say that the function decreases in the region minus infinity to minus 3 upon 32 and will be increasing when the values for x greater than minus 3 upon 32. So, minus 3 upon 32 to infinity, the region is, the function is increasing, and from minus infinity to minus 32, the function f(x) is decreasing function. I hope you understood how we solve this numerical. Now let's solve the next numerical, and wherein the function given to us is f(x) is equal to minus 5x square plus 7x plus 8. So, we again find the derivative. So, f dash x of this expression, that is minus 5x square plus 7x plus 8, will turn out to be minus of 10x plus 7. Now, for the function to be increasing, it should be greater than 0. This implies that x should be rearranged, should be greater than minus 7 upon minus 10, that is x should be greater than 7 upon 10. So, so that means x should be greater than 7 upon 10. Apart from this, for decreasing function, you need to calculate f dash x should be less than 0, and that means minus 10x plus 7 should be less than 0. That means x should be less than 7 upon 10. So, that means by solving this expression, you can always say that if x is less than 7 upon 10, then and f dash x is less than 0 if x is greater than 7 upon 10. So, we can find the regions, that these are the regions in which the function is increasing and decreasing. So, this is how you can solve the numericals and apply the understanding of the differentiation to find the increasing and decreasing functions. And I again recommend you to solve more and more numericals given into your self-learning materials, so as to have better understanding of the concepts. This is all about this part of the increasing and decreasing functions, and in the subsequent session we are going to discuss how to determine the local minima, local maxima, and many more details. Thank you.